Welcome to I think it's our seventh learning workshop, our sixth or our seventh, one of those two. Today we are going to be dealing with gases and the gas laws. So we have quite a few things to go over. So we'll go ahead and just dive right into this. That's our sixth learning workshop. Okay. So first things first. Kinetic molecular theory of gases. So there's 5 main tenets of the kinetic molecular theory of gases, and I'm sorry they all kind of like came out right up front. I need to go back and put some animations in here so you can just get them one by one. But essentially, gases consist of very large numbers of very small particles. So the particles of gases are in continuous random motion, and there's a lot of these particles, but they're spread out quite a bit. To the point where number 2 is also true. The combined volume of all the particles of a gas is negligible relative to the total volume of the container. For example, if I was to have, like, say, for a container like this of a gas, okay? If I was somehow able to compress all of those particles of gas in that container into one small, tiny spot, or if I was able to compress all those molecules into a solid, that solid might occupy that much, that tiny little green spot. So, yeah, and even that's kind of an over-exaggeration because it wouldn't even occupy that much. So, because there's such a small actual volume of these particles, because the particles are so spread out, we basically consider the particles to have no volume. So their volume is effectively negligible compared to the volume of the container. Now, the principle number 3 is that attractive and repulsive forces between gas particles is negligible. And this is because the gas particles, as opposed to the particles of a liquid and the particles of a solid, they are moving so fast that they don't really have time to stick together. So let's say, for example, you have a magnet, okay? If you put that magnet close to a piece of metal, especially if it was a small piece of metal, like a nail, that metal would probably get stuck to the magnet. It would get pulled into the magnet. You could even potentially lift it up from a table. Okay? But if you fired a bullet such that it went right past the magnet would barely have any effect because they're so fast. The bullet is so fast compared to the like, for example, the nail, that the magnetic force of the nail, the attractive force, the magnetic force of the magnet rather, the attractive force is only acting on that bullet for such a small amount of time, for such a small fraction of time, that it barely has any effect whatsoever. So the same thing is true as gas particles. These things are moving so fast that even if they actually hit one another directly, just like even, for example, if the bullet hit the magnet itself, it would just bounce off the magnet. It wouldn't get stuck because the attractive force of the magnet is just simply not strong enough to be able to handle all the kinetic energy that's coming from that bullet. So gas particles don't really have any attractive or repulsive forces that are effective. So we treat them as if they have no attraction towards one another in most cases. Number 4, energy can be transferred between molecules during collisions, but as long as the temperature remains constant, the average kinetic energy of particles remains the same. So the collisions are elastic. So basically, Even though, for example, if I have one particle that slams into another particle, the particle it hits might end up getting more energy and it might get less, but the overall average energy of all the particles in the system remains constant. And that brings us to number 5, that average kinetic energy of the particles is proportional to the absolute temperature. Temperature is a measure of the average kinetic energy of the particles. So it's not a measure of the total energy, it's a measure of the average kinetic energy. This is why there are some things that cool down very quickly, like aluminum foil or even gases. They cool down and warm up pretty quickly. But there are other things that take a very long time to warm up and a very long time to cool down, like water. That is because the particles in water are very dense. They're very tightly packed. So if the average kinetic energy of the particles is the same as that of the average kinetic energy of the particles in the gas, well, because the particles are so tightly packed in water, water actually holds a heck of a lot more energy than the air at the same temperature. That's getting into a little bit of something that's a little bit more complicated and we don't really need to focus on here, but as far as you're concerned, it's important to understand that the temperature of any substance, or especially of gases, is proportional to proportional to the kinetic energy. If the particles are moving faster, the temperature is higher. If the particles are moving slower, the temperature is lower. Does that make sense? Any questions on those? Does anybody need more time to write anything down? Or are we good?
Did you say you were sending the PowerPoint or something?
I will be posting the PowerPoint, yes. All right, cool. So let's go ahead and continue, if that's okay. So gases have 4 characteristics that we're really going to focus on with all of our gas laws. Volume, how much space it takes up, and usually the standard unit for that is in the liters. There's pressure, and pressure is interesting because pressure is basically based on the force exerted by a gas based on how many collisions it has with the container. So like, for example, if you have a gas, so gas particles are constantly, whoops, let me erase that, or undo. Oh, I guess I can't. Let's try that again. So if a gas, oh, what is it doing? Try it again. I'll do it up here. So gas particles are constantly slamming into the walls of the container. Constantly hitting the walls of the container. I don't know why it keeps doing that. And every time it strikes the wall of the container, it exerts a force on that container. So that force is called pressure. Because it's a combined total of all the force of all the particles smashing against the walls of the container at any given moment in time. So that's what causes the pressure. It's these little particles, these little gas particles that we can't even see, smashing into the walls of the container. So standard unit is 1 atm, and that's essentially the amount of pressure that we would experience at sea level from the air. We oftentimes forget this, but essentially on Earth we're standing at the bottom of a very tall column of air. So, here's U on the bottom of the screen. Here's U. And then there's this huge column of air above you, all pushing down on you. So, and of course the air is all around us and it's pushing down. So that huge column of air is exerting a pressure, and that pressure is approximately 1 atm. Okay. Then there's temperature, which we already mentioned is the average kinetic energy of the particles. Kelvin is the standard unit that we need to use. We always use Kelvin when we're doing the gas laws, never Celsius. Always use Kelvin. And the reason is because Kelvin is the absolute scale. While some of the other scales, based on where they set their 0 point, these can either be these can be positive or negative because of where they put their 0 point. Kelvin can only go from 0 to positive numbers, which makes sense because can you have less than 0 energy? Can an atom have less than no energy? What do you think?
No.
Is it possible to have less than 0 energy?
I think no.
Oh, Linda, are you talking? I can't hear you.
I said no.
Okay, cool. Yeah. Yeah, it's not possible to have less than 0 energy. And so our calculations with our gas laws get all screwed up if we're not using Kelvin, the absolute scale. All right, and then of course, finally, the other characteristic of a gas that we're going to be paying attention to with our gas laws is the number of atoms or molecules, or N, which we usually refer to in terms of moles, because a mole is 6.02 times 10 to the 23rd atoms or molecules. All right, cool. So let's get to our first gas law. This is Robert Boyle, our good friend from Ireland. He established that pressure and volume are inversely related at constant temperature. In other words, if you increase the pressure, the volume goes down. If you increase the volume, the pressure goes down. And the equation for that is P1V1 is equal to P2V2. Because the pressure times the volume equals a certain constant. So if whenever you increase the pressure, the volume goes down, so you multiply them together, you still get the same value for K. If the pressure was 4 and the volume was 1, if I decreased the pressure to 2, the volume would increase to 2, and I'd end up getting the same value for K. Pressure and volume is constant. Pressure times volume is a constant, and therefore P1V1 is equal to P2V2. So here is kind of a demonstration of that. So if the volume is 1 liter, pressure is 1. If you push and apply more pressure, apply 2 atm, it squeezes the volume into a smaller space. Just like if you're packing a suitcase for a long trip, if you want to fit more into the suitcase, you have to apply extra pressure. You push it down and then stuff more into it. So this is a good example of graphically what this looks like if you graph pressure and volume. You see it's an inverse relationship. As the volume increases, the pressure decreases, and as the volume decreases, the pressure increases. Okay. Then we have Charles' law. And feel free to stop me if I'm going too fast, or let me know if I'm going too slow. But Charles' law, basically, the volume of a gas varies directly with absolute temperature at constant pressure. So what that means is if you increase the temperature, if you make it warmer, then the volume is also going to increase. You can actually test this out on your own if you want to. If you have a balloon filled with gas and you blow up a balloon, put it in the freezer and let it stay there for a while, and then see what happens to it. You'll actually find that it shrinks. And then when you pull it out, it'll start expanding again as it warms up to the regular air temperature. So if you increase the pressure, the volume increases too. If you decrease the pressure, the volume also decreases. And it's a direct comparison. So if you double the temperature, you double the volume. You triple the temperature, you triple the volume. It's proportional. This is an example of that. You double the temperature from 200 to 400 by adding heat, then you actually double the volume, as long as the pressure remains the same. Notice the pressure in this case remains the same. Charles' law assumes constant pressure. It assumes constant pressure. It also assumes the same number of gases. So it also assumes a closed system. So no gas is added or taken away. No gas is added or removed. Likewise, Boyle's law assumes that no gas is added or removed, and Boyle's law assumes that temperature remains the same. Cool. Please feel free to raise your hand if you have any questions on anything. Here's a graph of Charles' law. You can see it's a straight line. Notice that with Celsius, and this is actually how they discovered absolute zero, the minimum temperature that anything can be. This temperature here is absolute zero. And absolute zero is roughly negative 273.15 Celsius. Because that's the theoretical temperature at which a molecule or atom or whatever would have zero energy, no energy. Now we've never actually reached absolute zero, but that's the theoretical temperature at which there would be no energy present in the molecule. But see that nice straight line. Now this strange looking fellow is Avogadro. You've heard of him before. Had that crazy number. He's got strange eyes too. All right. At constant temperature and pressure, the volume of a gas is directly related to the number of moles. So the more moles you have, the greater the volume will be at constant pressure. So it assumes constant pressure. It also assumes constant temperature. So constant temperature and constant pressure. So once again, you double the moles, you double the volume. You have the moles, you have the volume. It's a direct relationship. One mole, 2 moles. 2 moles, you double the gas. Then we have Gay-Lussac's law. Joseph Louis Gay-Lussac. At constant volume, pressure and absolute temperature are directly related. As temperature increases, so does the pressure. Okay, so in other words, you double the pressure, you double the temperature will also double, as long as there's constant volume and, even though it's not mentioned, constant amount of gas. So in other words, you're not adding or taking away any gas. Amount. Constant amount of gas. Cool. Next. That brings us to the combined gas law. So the combined gas law basically puts everything together into a single equation. It combines Boyle's law, Charles' law, Gay-Lussac's law, and Avogadro's law. So P1V1 over N1T1 is equal to P2V2 over N2T2. Now in truth, for the gas laws, you can actually choose to not memorize any of these other ones and just memorize this one gas law, because this one gas law contains all the others. If the pressure and the temperature are the same, then they're constant, then you can ignore pressure and temperature, and you have Avogadro's law. If the number of moles and the temperature is the same, then you have Boyle's law. If you have the volume and the temperature, well, actually, if you have the volume and the temperature staying the same, that's actually Dalton's law, which we're going to actually go over in just a second. But if you have the volume and the number of moles law staying the same, then you have Gay-Lussac's law. So all of the gas laws are basically represented in this one law. So it can be really helpful to remember this one combined gas law. So let's do some practice. Okay. There's 10.2 liters of a gas expands to 2.05 times 10 to the 5th milliliters. If the temperature is raised from 24.5 degrees Celsius to 98.0 degrees Celsius, what would the new pressure be if the original pressure was 742 millimeters of mercury? Okay. So what do you think? What would I do here? Any idea?
Okay, we've not done temperature. We have not done gas in my class, so
Okay.
we're just meeting it for the first time.
Okay. So, well, here's what I'd recommend. This is how you should. I would recommend approaching it like this. First, list out your variables, and try to see if you have one set of conditions or two sets of conditions. So, do I have one volume or two volumes?
You have one volume.
Actually, I have two volumes. These are both
What's
volumes, right?
Oh yeah, sorry.
And do I have one temperature or two temperatures?
You have two temperatures from this to this.
Two temperatures, yep. This one and this one. The only one I don't have is two pressures, but it is asking for the new pressure, and it gives this as the initial pressure. So I see that I'm going to go ahead and list out my variables. I have my combined gas law, P1V1 is equal to N1T1. And I can see if there's anything that's changed. So what's changing and what's staying the same? Is there anything that remains constant here? You can assume if it doesn't mention something, then that probably remains constant. So does anything remain constant? Does anything not change here?
I would think everything changed.
Everything changes except it doesn't talk about the amount of gas, right? It doesn't say that you add gas or you take away gas, right?
Yeah.
So the number of moles is actually going to stay the same. So I'm going to use P1 V1 is T1 over T1 is equal to P2 V2 over T2. So the first thing I'm going to do is I'm going to list out my variables. I have P1, V1, T1, and I have P2, V2, and T2. I like to list my variables because it helps me to organize my information and it makes it easier to solve. So remember the P1, V1, and T1, these are all your initial values. So what's my initial pressure? What's my initial starting pressure?
742.0.
Yeah, 742.0, very good. Millimeters of mercury. And what's my initial starting volume?
Initial volume is 10.2 L.
Yes, it's 10.2. 10.2 is expanded to the other amount. So 10.2 is what I'm starting with, liters. What's my initial temperature?
Initial temperature is 24.0 Celsius.
Did you say 24.5?
24.5, yeah.
Yeah, it's 24.5 degrees Celsius. That is our initial temperature. All right, now what's the final pressure, or do I not know that?
98.0. Oh, pressure? No, we don't know that. That's what we're looking for.
Yep, that's what we're looking for. And what's the new volume? What's the final volume?
2.05 times 10 raised to the power 5. What's that? Can we calculate that one? 2.0
Yeah,
times 10 raised to the power.
it's the 2.05 times 10 to the fifth, right?
Mm-hmm.
Milliliters. And what's the final temperature?
98.0
What's the
Celsius.
final temperature?
98.0.
Yeah, 98.0. Now here's the thing. If I'm looking at my volume, what's wrong with my two volume measurements?
They are not, how have I said now? Are we supposed to convert this other one to?
Yeah, they're not the same unit, right? The units
No.
don't match. So because the units don't match, we have to actually convert one to the other. Now it doesn't matter which one we convert. We can convert the liters to milliliters, or we can convert the milliliters to liters. In this case, I guess I'll just go ahead and convert milliliters to liters. So I'm going to go ahead and say, okay, I have milliliters down here, and I have liters up here. Milli means 10 to the negative third, so 1 milliliter is 10 to the negative third liters. And if I multiply that, that's going to give me 2.05 times 10 to the second, or 205 liters. And then the okay, so I have my volume units that match. Are there any other problems with my units, or can I go ahead and plug it into the ideal gas law? I mean, the combined gas law equation. Yeah, the temperature has to be in Kelvin, right? I can't have Celsius because Celsius technically can be negative, and it's also not proportional. Celsius, it doesn't start at 0, it starts at negative 273, so as the lowest temperature. So I'm going to have to add 273 to each of these. And so I'll add 273 to this and 273 to this.
To get Kelvin.
And what do you get for Kelvin?
98.
This one should be 371 Kelvin.
71. Yeah,
Mhm.
371.
And then the one above, 297.5.
297.5.
Yeah. So now I have my Kelvin, and I have my volumes matching, and I have the pressure. Now it doesn't ask me what unit it wants pressure in, so I'll just go ahead and leave the unit the same. That's fine. I know now that I'm looking for P2. I write the equation P1V1 over T1 is equal to P2V2 over T2. Sorry. I think the easiest way to deal with this is to go ahead and do cross multiplication. Go ahead and use cross multiplication, okay?
So why did you change the formula? What about the N1, N2? We don't have that, right?
Because it's constant, so it cancels out. It's not part of the equation. If the amount of gas is not changing,
Okay.
if we're not adding or taking away gas, you can ignore the end because it's going to be the same number, and so therefore it'll cancel out.
Okay.
Anything that's constant is going to cancel out.
Okay.
So the easiest way to do this type of problem is I think it's to go ahead and cross multiply first, and that's going to give you P1 times V1 times T2, and that gives you P2 times V2 times T1. Now if I want to solve for P2, if I want to get P2 by itself, what do I have to do?
You try to put the V2 over T2 on this other side so you could isolate. So you cancel out with V2 T1.
And how do I cancel out V2 and T1? What do I have to do?
You put V2 T1 over here and you put it on both sides.
You divide by V2 and T1 on both sides, right? So now I have, the P is still there, sorry.
So you
So
have
P2 is equal to
P2
P1
equals to
V1,
P1 V1 T2 over V2 T1.
so now I'll just go ahead and plug in my numbers.
Yeah.
So my P1 is 743, or 742, sorry, 0.0 millimeters of mercury.
Times
Times what did you say?
times V1 is 10.2.
10.2. Your voice is a little hard to hear, sorry. Very quiet.
10.2, sorry.
That's okay. And that's going to be times the temperature, which is, which one?
Times the temp. T2 is 371.0
Yeah, T2 or 371.0.
over
So
V2.
now I'm going to divide by V1. What's my V1?
No, V2, you mean?
Or my V2 rather?
205 liter.
Uh-huh.
205 liter times
And then I
T1,
also divide by my T1, which is?
297.5.
Yeah, 297 or 0.5. And that's Kelvin.
205.
So here's the cool thing. If we go ahead, we can now cancel out all the units that are on top and bottom. So the liters cancel out, and the Kelvin cancels out. And so I'm left with millimeters of mercury, which is what I want. So that's perfect. So 743 times 10.2 times 371 divided by 205 divided by 297.5. What does that give you?
At the bottom, you have 20987.5.
Mm-hmm.
Then at the top, you have 4. Hold on. I'll give you that just now. Times
And I'll
10.
admit, I don't usually multiply and divide them separately. I just multiply everything on top and divide by the bottom in order to just kind of like uh, save time, make it as quick as possible.
Okay. 2807. Hold on. 0706. divided by,
So let me know when you have something.
okay, so 0987.5 equal to 46.04.
46.04, yeah. And with the only three significant figures, the 10.2 liters, that means this is just going to be 46.0. 46.0 liters. No, not liters. What am I talking about?
Liters, the pressure is mmHg.
Yeah, you got it. Yeah. The only one that didn't cancel out was mmHg. mmHg. Millimeters of mercury. Very good. What do you think? Do y'all want to take a stab at number 2? Or do you want to do that together? How comfortable do you feel?
We were together in God's family.
You want to try doing it together? Okay, no problem. All right, so with this one, it gives me pressure of 12.4 atm and a temperature of 36. By how much must the temperature change for the pressure to fall to 2874 millimeters of mercury? So in this case, if I'm looking at my original ideal gas law equation, or not ideal gas law, combined gas law equation, P1 V1 is equal to N2 N1 T1. Got it? And that's equal to P2 V2 N1 T2, or N2 T2 rather. Now let me ask you, it gives us pressures, right?
As 2080,
Mm-hmm.
2874.
What's remaining constant, or what's not being shown here in this problem?
We have only one temperature.
What'd you say?
We have only one temperature and
Yeah,
one.
yeah. Well, there's one temperature, but what's not changing here? Volume. Very good. Dan, you're absolutely right. Volume is not changing. There's no mention of volume, so we can assume that the volume is remaining constant and take that out. What else is not changing, or what else doesn't give any information as to whether or not it's changing?
The temperature.
Pressure. Well, it says we have a temperature, and then it says by how much must the temperature change. The temperature's not
Oh, yeah,
constant. It's changing.
it's changing. Yeah.
So what else is constant though? The pressure, the temperature, or the number of moles?
Michael, I don't really know.
Are you adding or taking away gas? Are we adding or taking away any gas?
By how much must the temperature change for the pressure
I can
to
barely
fall?
hear you, Linda. You're far away from your microphone.
No, I'm just reading the question. Say, by how much must the temperature change for the pressure to fall to this?
Yeah. So, and yeah, Leon got it. It's moles. Moles is not changing here. There's no change in the gas because no gas is being added or taken away. The only two things that are changing are pressure and temperature. So the equation that we're really going to use here is P1 over T1 is equal to P2 over T2. Anybody know what kind of what law that is? It's okay if you don't. Yeah, it's not Boyle's law. It's actually
That would have been Charles' law.
that's not Charles' law either. Charles' law is volume and temperature. That means it must be Gay-Lussac's law. Yeah. Yeah, it's Gay-Lussac law.
Gay-Lussac.
Now we can go to, we'll list out the variables here. So what's the initial pressure?
2874. No.
Yeah.
12.54.
12.54, yep. 12.54 ATM is the original pressure. And what's the initial temperature?
36.8.
Yeah, 36.8. Whoops. Messed that up. 36.8 degrees Celsius. Oops. And what's the final pressure?
2874. P2 is 2874 mmHg.
2874 millimeters of mercury. And the final temperature is what we're looking for. All right, so here we go. Is there any problem with our pressures that we have to fix? Yeah, they're not the same, right? And actually, you may want to make note of this. These are pressure units that are equivalent. I'm going to put this at the top of the page. 1 ATM is equal to 760 millimeters of mercury, which is equal to 760 torr. A torr and a millimeter of mercury are the same thing. Which is equal to 101.3 kPas, or kilopascals. So those are the ones that you're going to be probably expected to know, at least the ATM and the millimeters of mercury and torr, because those are the ones that are used most commonly when we're dealing with chemistry. Okay. So if we want, we're going to have to convert one of these pressures to the other unit. We need the pressures to be the same unit. Doesn't matter which one, but they need to be the same so that they can cancel out. So I'll convert millimeters of mercury to ATM. Millimeters of mercury as the unit comes on the bottom. ATM comes on top. And therefore, according to the list up above, 1 ATM is 760 millimeters of mercury. So then you just divide 2874 by 760, and what do we get?
Two eight seven four divided by 760.
Yep.
That's 3.781 or 3.782.
Yep. Very good. 3.78. So an ATM is a big unit. Millimeters of mercury are much smaller by comparison, but 3.781 actually, it would be 3 significant figures. 8 or 4 significant figures.
Two, it would be 3.782 because you're going to approximate.
Oh, okay. Whoops. 3.782. Good call. So 3.782. So that's ATM. Okay, and then we also have to convert the Celsius, right? Because we can't use Celsius with the gas laws, so what do we have to do?
It's 309.8.
Yeah, we have to add 273. And that sounds right, 309.8. This is degrees Celsius. This is Kelvin. Okay, so after we have those down, now we can go ahead and solve. Like I said, I like to cross multiply this equation because I think it's easier to work with. So it's P1 times T2 is equal to P2 times T1. In this case, we're solving for temperature. So what do I have to do? Solving for T2.
Yeah, you're looking for T2, so you put over P, so you put P1 times T2 over P1 divided, then you put it on both sides, P1 on both sides. You divide by P1 on both sides.
Divide by P1 on both sides, that's right. So P2 times T1 over P1. All right. Now all you have to do is plug in the numbers. So P2, of course, is 3.782 times T1, which is 309.8, and then divided by P1, which is 12.54. And what do you get for your temperature?
93.43.
93.43. Yep, sounds about right.
K, 93.43 K.
Yeah, it's a really small number. Well, it's a really small number for a temperature. To give you an idea of how cold that is, even in the middle of winter in the coldest part of the Antarctic, it doesn't get that cold here on Earth. That's an extremely cold temperature. Very good. All right, let's jump into the next one, shall we? Well, the next topic, that is. And before we do that, though, any questions on this? Does this make sense?
I think it's practice that will make us better in this one.
Yeah. All right, cool. So now for the ideal gas law. So when we put together that combined gas law, what we came to realize is that P1 V1 is equal to P1 V1 over N1 T1 is equal to P2 V2 over N2 T2. It's actually a constant condition that this ratio P V over NT for any conditions is a constant. This constant R is referred to as the ideal gas law constant. And it gives us this new equation that we can use. If we just have one gas or one set of conditions that we're looking at, in other words, we're not changing something, we're just looking at a set of conditions of a particular gas. So a particular gas is existing at certain conditions. If we know any three of those conditions, we can find the fourth. If we know the pressure, volume, and the number of moles, we can find the temperature. If we know the temperature, volume, and the number of moles, we can find the pressure. Usually where this is useful is to find the number of moles of a gas, because usually we can control the volume and we can measure the pressure and we can even control the temperature to some degree. But it's really hard to measure the moles of a gas directly. We can't really necessarily weigh a gas real easily. Weighing gases is something that's very challenging. So this is a really great way to calculate the amount of gas present if I know these other three variables: pressure, volume, and temperature. Another gas law that's going to be that you're going to need to know, unfortunately this is actually one of the simplest of them, is Dalton's law. And Dalton's law basically states that the total pressure in a container is the sum of the pressure that each gas would exert if it were alone in the container by itself. So in other words, the total pressure is the sum of the partial pressures. If I have a mixture of 5 gases, the total pressure would be the pressure that gas 1 would exert plus the pressure of gas 2 plus gas 3, gas 4, and gas 5. And this is basically because for each gas, the pressure is equal to the number of moles times the R, the T, and the V. And for a gas under a particular set of conditions, the gas constant stays the same. If they're all under the same conditions, they have the same temperature. And if they're all in the same container, then they have the same volume. The only thing that's different between these guys is the number of moles, because they're different gases. If I have, like, say for example, 1 mole of helium, and I combine that with 3 moles of oxygen, the partial pressure will be the pressure of the helium plus the pressure of the gases, pressure of oxygen. They're all in the same container. They all have the same temperature. The constant ideal gas constant is the same. The reason they have different partial pressures is because there's different amounts of moles of each of them. So this is an idea. So let's say, for example, you had 2.9 atm worth of hydrogen gas. It's about 0.6 moles of hydrogen gas. And this is a 5.0 liters at 20 degrees Celsius. If I have 7.2 atm that's being generated by 1.5 moles of hydrogen gas, then if I add the pressures together, 2.9 plus 7.2, that actually gives me the total pressure that both gases, when combined in the same container, would exert. When combined in the same container, they exert a total of 10.1 atm. And notice the mole ratio is the same as the pressure ratio. Or, as I mentioned before, in a roundabout way, that P1 over N1 is equal to P2 over N2 is in a way an expression of Dalton's law. All right, so let's take a look at some practice problems. Go ahead and drop this. And we're going to pull up some practice problems. I have them on the Gas Workshop outline, Gas Logs Workshop outline that is saved with you. I'll go ahead and share this. Linda, if you're saying something, I can't hear you. I'm sorry.
No, I wasn't saying anything.
Okay. I just saw your microphone was on. I was like, oh, I don't know what she's saying. Hmm. Linda, can you talk for a second? I want to see if my microphone's working properly.
Your microphone is perfect.
Okay, awesome. Thank you. Appreciate it. Okay, so let's take a look at some more practice problems. So it says a helium balloon of 1.5 liters at 25 degrees Celsius is released into the air after climbing to a high altitude where the pressure temperature is negative 15 degrees Celsius. What is the volume of the balloon? Assuming no change in pressure. So what type of equation are we going to be using here? Oh,
No change in pressure.
so if it's a helium balloon, is the amount of gas changing? Okay, somebody said something. Charles law. Yeah, in this case, we're going to deal with, it's going to be Charles law. And Charles law ignores pressure. It only relates the the volume and the temperature. So I have volume 1 over temperature 1 is equal to volume 2 over temperature 2. I'm actually going to zoom this in, make it a little bit more viewer friendly. Bam. Look at that. So nice. Okay. So now I'm going to go ahead and list my variables. What's V1? What's my initial volume? Yep, 1.5 liters. What's my initial temperature?
Temperature is 25 degrees.
Yeah, 25 degrees. And what's my initial volume? Or what's my final volume, rather?
Final volume was what we're looking for.
That's what you're looking for. Yeah, Gianna's watching Christmas videos. Sorry, my little girl just came in. One of the blessings and difficulties of working at home. Um, I get to see my precious little daughter, but she sometimes interrupts. All right, and what's the final temperature?
Minus 15 degrees.
Yeah, minus 15. Good call. I think Leanne beat you on that one. All right, so is there any issues with this particular problem? What am I going to have to do to solve for this?
First of all, we need to convert the Celsius to Kelvin, which turns to 298 degrees.
Absolutely. We need to convert Celsius to Kelvin because we cannot do anything with it in Kelvin like this, or in Celsius. So yeah, this will be 298 Kelvin. And the other one will be what?
I'm trying to calculate that one.
258. Very good.
258.
Yeah. So then all we have to do is recognize that we can go ahead and cross multiply this equation. We're solving for V2 is V1 times T2 is equal to V2 times T1. And
Cross multiplied, right? Yeah.
yeah, that's multiply. Yeah, just it's a little multiply sign. If you see a little dot in the middle, that usually indicates a multiply sign. I know that in certain other countries, sometimes a dot in the middle means a decimal point. Um, I'm not sure if that's something that you've seen as a decimal point in the past, but in American mathematics, a dot in around the middle refers to multiplying the two. So yeah, I might use a time sign in the future, but okay, let's go ahead and we solve for V2. That means we're going to get V2 by itself. So you guys already seem to have pretty good algebra on this. You know that we need to do what? To solve for V2, what do we need to do?
So stuff for V2.
Mm-hmm. Yes, indeed.
You divide by.
Yeah, we divide by T1. Very good. And then we have V2 is equal to V1 times T2 over T1. And then I just plug in the numbers and solve. My V1 is 1.50. Now, admittedly, if you get to this point, you may be like, oh, I don't need to write down the numbers again. I already have the numbers right there. I know what to do. I'll just plug it in and solve. And you can definitely do that. That's totally fine. I'm just going to go ahead and write the numbers to make it very clear. And yeah. And on the bottom, of course, we're going to have the 298. Now, what does that give me for a final volume?
1.298. Then if you approximate, it will be the three significant figures will be 1.30, I think.
Yeah, 1.30 liters. Very good. Very good. Well done, all. I'm super proud of you guys. All right, excellent. Now, let's go ahead and proceed to dive into number 2. So the gas sample has a pressure of 2.45 atm and a volume of 15 liters. If the sample is compressed to 2.5 liters, what will the pressure be? So, what law are we going to use for this particular problem? In this one, you see that pressure appears to be changing, volume appears to be changing, everything else seems to be constant. So what law would that be? Yeah, very good, Leanne. Boyle's law. So it's essentially there's no change in the moles of gas, there's no change in the temperature. No moles, no change in temperature. That means it's P1V1 over P2V2 or Boyle's law. So let's go ahead and we'll do Boyle's law. P1V1 is equal to P2V2. In this one, they've made it a little bit easier because the units are the same. So this is great. I can just list out my variables. My initial pressure, 2.45. atm. My initial volume is what?
Initial volume.
Yep, 15 liters. What's my final pressure?
Final pressure. That's what you're looking for.
That's what I'm looking for. And what's my final volume?
Final volume is 2.5.
Yeah, 2.5. Very good. So now all we have to do is recognize we're solving for P2. To get P2 by itself, I'm going to divide both sides by V2. And then from there, I can go ahead and cancel out V2. P2 is equal to P1 is 2.45 atm, times V1, which is 15.0 atm, 15.0 liters rather, and divide that by V2, which is 2.5 liters. And what does that give you for your pressure? Very good, 14.7 atm. Except with the only two significant figures for that 2.5 liters, I'd have to round it to 15 atm. Any questions? All right, cool. I'm going to go ahead and skip number 3 because it's another one of those types of questions that we've seen before. I do want to talk about number 4 though. So number 4 says, what is the volume of 3.25 grams of N2 STP? There's actually two ways to solve this problem. There's the easy way and the hard way. I'm going to show you the easy way. I actually might show you both, but your professor is going to expect you to know this following relationship. STP means, and actually I'm going to go ahead and insert a little text box here. STP, oh, I don't want that. Okay, I changed my mind. That was a bad idea. STP means standard temperature and pressure. I'll just do this. Okay. STP means standard temperature and pressure. Standard temperature is 0 degrees Celsius. Also known as 273 Kelvin. Right, those are the same. Standard temperature is 0 degrees Celsius, otherwise known as 273 Kelvin. And standard pressure is 1 atm. Standard temperature is 0 degrees Celsius, standard pressure is 1 atm. Okay. And this is important. At STP, 1 mole of any gas has a volume of 22.4 liters. And I'm actually going to bold this and highlight it. 1 mole of any gas has a volume of 22.4 liters. In other words, you have new conversion factor. In other words, you have 1 mole on top is 22.4 liters on bottom. Or you can have 1 mole on bottom is equal to 22.4 liters on top. And so these are both valid conversion factors that you can now use to convert between moles of a substance and volume of a substance, provided it is at STP. Now, if it's not at STP, you will have to use your whatchamacallit? You'll have to use your ideal gas law. And you could still use the ideal gas law for this. It would just take a little bit longer. Okay, so let's go ahead and solve this using the 3.25 grams N2. Okay, so I know that 1 mole of any gas is 22.4 liters. So what's probably the first thing that I'm going to want to do with those grams? Yeah, well, okay, I can't convert the grams to liters. What can I convert the grams to? I don't have a way to convert grams to liters.
Can you convert it to moles?
Yeah, I have to convert them to moles. Exactly. So I can't convert the grams to liters, but I can convert them to moles. So that's what I'm going to do. So I'll have grams of N2 on the bottom, and I will have, oops, no, moles of N2 is going to go on top. So a 1 mole of N2 is, what's the conversion factor that allows me to convert between grams and moles? How many grams of N2 is equal to a mole? Where could I find that? Could you say that again? It was a little bit distorted.
Is it 20? Is it 22.4? No.
Okay. Your sound is kind of a little bit crazy right now, so I'm not sure. It's really hard to understand you. But I think what you're trying to say maybe is 28.02. Yeah, you'd have to use the molar mass. And since nitrogen on the periodic table has a mass of 14.01, and there are 2 nitrogens here, this is going to be 28.02. All right, good deal. Well, now that I have moles, what can I convert the moles to? What can I convert the moles to? Liters. Yeah. So I have to convert the moles to liters. So I will go ahead and use the conversion factor. I'll put moles of N2 on the bottom. And then I can say I have 22.4 liters of N2. And then I'm done. That's all I have to do. 3.25 divided by 28.02 times 22.4. And what do I get for my answer? You can type it into the chat. And Linda, forgive me, I'm going to go ahead and mute your microphone because it's really badly distorted and it's hard to make anything out. Sorry about that. But yeah, feel free to type it into the chat. Yeah, about 2.6, 2.60. That sounds about right. Very good. 2.60 liters of N2 gas. Awesome. All right, let's skip ahead and let's do the next one. It said a mixture of gases of H2, N2, and argon have a pressure of 1,515 millimeters of mercury. If the partial pressure of H2 is 456 millimeters of mercury, and the partial pressure of N2 is 101 millimeters of mercury, or 1.01 atm rather, what is the partial pressure of argon? So the mixture has a total pressure of 1,515 millimeters of mercury, and it gives you the partial pressure of hydrogen and nitrogen. So what am I going to need to do here? This is going to be an application of what gas law? What do you think? What gas law would I use? Yeah, Dalton's law. So effectively, I'm going to end up using Dalton's law here. And it's going to be P total is equal to the pressure of H2 plus the pressure of N2 plus the pressure of argon. All right, here's the deal. Pressure of H2, pressure of N2, pressure of argon. What is the pressure of each of these? Oh, well, here's the thing. If I'm looking for the partial pressure of argon,
Mike, I was asking you, is that the sum of, you said PT times, what's that?
I'm sorry, I can't make out what you're saying.
The very first one you wrote, you said PT times T. Is that it? What's that? I didn't get that.
Oh, the PTOT is the total pressure. P total
Okay, thank you.
is equal to PH2 plus PN2 plus PAR. Yeah. So, and the total pressure is given. Now, in fact, all the pressures are given in the same unit, millimeters of mercury, except for the N2. So what do I have to do? I'm going to actually make use of this equation.
You're gonna isolate them.
Well, yeah, I'm gonna have to convert the pressure of N2 from ATM to millimeters of mercury. So I have to convert the pressure from 1.01 ATM to millimeters of mercury. So my pressure of N2, I need to have all my units in the same, to be the same. So 1.01 ATM. I'm going to have to convert this to millimeters of mercury. And as I wrote before on the PowerPoint, 1 ATM is equal to 760 millimeters of mercury. So if I multiply that across, I should get what? Yeah, 768 millimeters of mercury. Now all I have to do is plug in my numbers and solve for the missing variable. So I have my total pressure, which is 1515. And I have my pressure of hydrogen, which is 456 millimeters of mercury. And I have my pressure of nitrogen, which is 768 millimeters of mercury. All I have to do now is to solve for the pressure of argon, which I don't know. So what would I do at this point? Yeah, just subtract. And what do y'all get for your pressure of argon? Yep, 291. Very good. Well done. Yeah. So the pressure of argon, if I subtract 456 and 768 from both sides, that's going to be 261 mmHg. Cool. And one more problem that we can go ahead and take a look at, because I think it's kind of a fun one. This says how many grams of dry ice or solid CO2 would be needed to fill 20 liters of container to a pressure of 2.5 atm if the temperature inside the container is controlled to be 50 degrees Celsius. Now, do you have one set of conditions here, or do you have two sets of conditions? When I say that, I mean, do you have one temperature or two temperatures, one pressure or two pressures, one volume or two volumes? What do you have here? Does it look like you're just dealing with one? Yeah, it's one set of conditions. Anytime you have a system where you're actually only dealing with one set of conditions, in other words, it's not representing any sort of change to the system, nothing's changing, it's just one set of conditions, then you're going to want to use the ideal gas law. And so the ideal gas law, of course, is PV equals nRT. PV is equal to nRT. And what's the initial pressure? Well, there's no initial and final, there's only one pressure. So I see that I have 2.50 atm for my pressure. And I also see that I have a volume of 20 liters. Hold on, Kiana. And then I have moles. I have the R value. And here's the thing, and this is why I oftentimes would like to go ahead and list out my variables P, V, N, R, T to get a clear idea of what I have, what I don't, and if I need to convert anything. So the pressure, of course, I've already said is 2.50 atm. The volume, 20 liters. And the number of moles, do I have the number of moles? Yeah, I don't, right? So that's going to be a question mark. And then R value, the R value would have to be given to you. The most standard value that's given for R, the one that you see in almost every textbook, is 0.0821 liter. And this is a unit. This is not like, these are not variables. Liter ATM per Kelvin mole. It has this really awful combined unit. Liter ATM over Kelvin mole. Whoops, moles, not mott. Okay. And then the temperature is 50 degrees Celsius. So can I use all these values as is, or do I have to change any of them?
You change the temperature to Kelvin, and you get 323 Kelvin.
Yeah, exactly. I have to change the temperature from Celsius to Kelvin by adding 273. That's going to give me a new temperature of 323 Kelvin. 323. So 323.0 to be precise, but I'm being lazy right now. Okay, so now I have all that I need to solve this. And it looks like I'm going to actually solve for moles. And you might ask, well, I'm actually looking not for moles, but I'm looking for grams, right? I'm looking for grams of carbon dioxide. So, but once I have the moles, I can solve for the grams, right? So I'll go ahead and solve for moles first. And I'll go ahead and put in my R value, which is 0.0821 liter ATM per Kelvin mole. Liter ATM per Kelvin mole. And then the temperature is 323 Kelvin. So all you have to do then is solve for N, the number of moles. And basically, so you divide both sides by 0.0821 and the 323, and that'll give you your moles. Oh, I said stop inking. Stop it. Stop. Copy. Paste. Ha! I did it. I didn't want to rewrite it. I was being lazy. Paste. So I divide both sides by that. And then that makes me very happy that I didn't have to rewrite that. This cancels out. And I get moles is equal to 2.5 times 20 divided by 0.0821 and 323. And what does that give me?
1.885.
Yeah. 1.8, yeah, 1.89 basically, right? 366, 1.89 moles. Very good. That's not the final answer, but that's 1.89 moles of CO2. I can then convert the moles of CO2 to grams using the molar math. Carbon is 12, oxygen is 16. 16 times 2 is 32. So 32 plus 12 is 44. So I get 44.01 grams of carbon dioxide is equal to 1 mole of CO2. And then I just multiply that out. And I should get about 83.0. 83.0 grams of carbon dioxide. 83.0 grams of carbon dioxide. Excellent. Now, I will say this. Some professors for the 1406 class do not require you to use the ideal gas law, the PV equals nRT one. Some of them, I think, might require you to use it, so I showed it to you just in case. But you may end up not ever needing to use it. However, I hope going through these problem-solving strategies and how to cross-multiply, list your variables, set up the equation, and all that stuff was helpful to you. And will make it easier for you when you actually have to go ahead and take care of it yourself, you know?
Yeah.
Cool. Well, thank you so much for coming. It was fun having you all here, and I wish you a great week. Don't forget, we will be having a test review for your upcoming test tomorrow, and have a great spring break if I don't see you before then.